So this is the very last topic in the iGCSE intro units. So this is 8D Cosmology key points. So let's talk about the different cards. So we've got cosmic microwave background radiation, or just CMB often called. That's the simple idea that when the universe was created, matter and antimatter, so it might be antiprotons and protons, came together. They annihilated. So when particles, antiparticles come together, they annihilate, they produce energy, but in the form of a wave. So the gamma rays are produced, and the energy there is a very short wavelength. That radiation is very short. But of course, if the universe is getting bigger and bigger, so expanding, it got longer too over time. So now those gamma waves appear as microwaves, and we actually pick them up as crackles, hiss, and interference on our radios. Now, two scientists called Penzias and Wilson, sometimes they talk about them, they found that these waves by using something called the Horn antenna. It's like a special microwave telescope, and it was all by accident, but it's pretty impressive because they have got evidence that proved partly that the Big Bang happened. So it's an expansion of the universe was proved by cosmic microwave background radiation. The other bit of big evidence that we've got to talk about is redshift. Now, redshift is when light of a specific wavelength is emitted from a distant galaxy and it becomes stretched because the universe is expanding. So a blue wave is emitted from a star, and then when it gets to Earth, it appears a little bit more red. Now, that's what we call a spectral shift. It's a little bit simplistic, that, because what we really mean is that say if light emitted from a star that contained calcium or hydrogen or iron or magnesium gave out these special spectral missing lines, what we're saying is that this one will be shifted just slightly over. So this one's green and it would still be green. That's red and is still red. This one is so like blue but might appear green, or green appears red. So we're shifting our wavelengths effectively, and that shift tells us that not only if we look at these spectral lines it tells you what the star contains, but if the reference pattern is shifted to the right, it tells us how far it's moving away from us. And the special formulas for that is that when a wave source is moving relative to an observer, there'll be a change in observed frequency and wavelength. So we've got the change in wavelength divided by the reference wavelength, which would be lambda naught. So that's the change divided by the original wave. So that's what's emitted. That's the shift effectively, divided by the speed it's traveling at over the speed of light. Simple as that. So it looks tricky. It's very straightforward when you do some questions. So that's a massive bit to prove this redshift or Doppler shift. And the Big Bang is really this theory that the whole of the universe began at a single point called a singularity, which was incredibly high energy, 13.8 billion years ago. Then we had a rapid expansion, which occurred from which all of the matter in the universe formed. The universe was very hot, around 4,000 degrees Kelvin, or 4,000 Kelvin, I should say, which has been cooling as it expands. And now the temperature is around 2.7 Kelvin. So we've cooled down massively. We've got these microwaves now that we're gamma, and we've got redshift, all proving that this Big Bang happened and the universe expanded. What you've got to be able to specifically do is work out redshift for galaxies. And so galaxies that move apart from each other. So there's the Earth, and we're part of the Milky Way, and we're in a local group. And these local groups move away from each other, and also galaxies move away from each other. So we see redshifted light in general from galaxies, because the tricky bit is you can do, in other specs, you look at where sometimes stars can come towards you, but we're just looking at when they go away, which is redshift. So there you go. That is Cosmology 8D done.